Good day, everyone. My report is about effects of power factor on voltage drop. So first, what is power factor? So power factor is defined as the cosine of the angle between the voltage and current, and it's represented by power factor is equals to cosine theta. In AC circuit, the voltage and current are ideally in phase, but practically, there exists a phase difference between them. The cosine of this phase difference is termed as power factor. It can be defined and mathematically represented as follows: power factor, power triangle, and impedance triangle. So another note here is another equivalent of power factor is active power, which is in watts, over the apparent power. So it will be discussed later on. So the power factor can be lagging, leading, or unity. So there are three types of there are kinds of power factor, and it is subdivided into lagging, leading, or unity. First is the lagging power factor. Lagging power factor is where the voltage, current wave, and phasor angle is wherein the current wave lags behind the voltage. So as you can see in this figure, the current lags behind the voltage. So as you can see here in the represented in the graph, there, the current lags. When current lags behind the voltage, the power factor of the circuit is called lagging. When the circuit is inductive, the PF is lagging. The loads such as the induction motors, coils, lamps, etc. are inductive and have lagging PF. Next is the leading power factor. This is where the current leads the voltage. So when you can see the difference in the graph and the angle representation between leading and lagging. So when current leads the voltage or voltage lags behind the current, the power factor of the circuit is called leading. When the circuit is capacitive, the PF is leading. So capacitive loads such as synchronous condensers, capacitor banks, etc. draw leading current. Such circuits have leading power factor. So as you can see here in the graph, the representation. Next is the unity power factor. So in his unity power factor, the current is in phase with the voltage. So as you can see in this illustration, the current is not totally in phase but almost near to 1 or near to the unity. So power factor is unity. Example is 1 for ideal circuits. When current and voltage are in phase, the power factor is equals to 1. So the power factor is equals to 1. Power factor cannot be more than unity. So it cannot be greater than 1. If your power factor is 1, it cannot be greater than 1. So practically, it should be as close to unity as possible. So it should be somewhat like the voltage and the current will not touch each other, as you can see in this graph. they are in phase but they are not perfectly in sync. So that's all for the power factor for the introduction. So if the power factor is low, following problems are encountered, or you can say it is the effects of lower power factor is showed in this presentation. So when the load current power in an AC circuit can be given as P is equals to V times I cosine theta. So therefore, the I or the ampere is somewhat proportional to the 1 over cosine theta. So cosine theta is equals to P over voltage times ampere, P over VI. So similar relationship can be derived for three-phase circuit too. We can see that current is inversely proportional to PF. So for example, consider that you want to transfer 10 kilovolts ampere power at 100 volt. If the PF is equals to 1, I is equals to P over V cos theta is equals to 10,000 volts ampere over 100 times the PF. So our PF is the cosine theta and it is 1 as given in this example. So the resulting current is 100 ampere. So if the PF is equals to 0.8, I is equals to P over V cos theta. So it's equals to 10,000 volts ampere over 100 times 0.8, and the resulting current is 125 ampere. So as you can see in here, the current drawn is higher for low power factor here. So you can see that the current in low power factor is higher compared to the power factor of 1, or which is near unity. So as stated above, for low PF, the current drawn is high. Hence, copper losses are I squared times R losses will also be high. This decreases the efficiency of the equipment. Overheating of the equipment, I squared times R losses produce heat. Hence, the temperature rise will be relatively more for low PF, which will further increase the stress on the insulation. So, as you can see in here, as the current goes higher, the copper loss also goes higher, and it decreases the efficiency of the equipment, resulting to overheating. More heat are produced, and the temperature will rise relatively more for low PF. So considering the size of the conductor, in the effect of the low power factor causes higher load current. If the load current increases, the size of the conductor required will also increase. This will further increase the conductor cost. So low power factor causes high current. So the better size or the bigger size of the conductor is required for it to satisfy the but it will increase the conductor cost. So you can call it as a benefit. In terms of kilovolts ampere rating of the machine, machines are not rated in kilowatts while manufacturing because the power factor of supply is unknown. Instead, they are rated in kVA. So according to definition, cos theta is equals to active power kilowatts over apparent power, which is the kilovolts ampere. Hence, the kVA rating is equals to 1 over cosine theta. Therefore, for low PF, equipments of larger kVA rating is needed. But larger kVA rating means larger size of the equipments. If the size increases, the cost ratio increases. So in terms of voltage drop, in an electrical circuit, voltage drop in an electrical circuit normally occurs when a current passes through the cable. It is related to the resistance or impedance to current flow with passive elements in the circuits, including cables, contacts, and connector affecting the level of voltage drop. So voltage regulation, it is defined as the difference between sending and receiving end voltage per unit sending end voltage. When power is transferred from one end to another, the voltage drops due to several reasons. This voltage drop should be within permissible limits. So as you can see in here, in the previous illustrations, P is equals to VI cos theta, so therefore 1 is proportional to 1 over V. So in short, for low power factor, current will be more and hence the voltage drop will be increased. Hence, the voltage regulation at low power factor is poor. So to summarize it all, low power factor means higher current, higher voltage drop, and the resulting voltage regulation of low power factor is poor. So it is most likely the most accepted and most accepted power factor should be higher or nearer to unity, as I've mentioned a while ago. Here you can see the voltage drop formulas and calculation for single phase circuits and three phase circuits. So as you can see here voltage drop for single phase, so this cosine theta is the power factor, and once we've compute, I should have provided an example, but I can't find anything. But as you can see here, this will prove the notion I mentioned a while ago, that as this power factor is lower, the voltage drop will increase, thus increasing the voltage, thus making the voltage regulation poor. So that's all, and thank you.